All right, so first of all, AgNO3, does this say AQ after it? That means it's dissolved, all right? So if it were to dissolve into its ions, the two ions that make it up are going to be Ag plus, and then I put AQ after it, plus, remember that's a polyatomic. Polyatomics, they stay together. I always write too big when I do these. The full ionic reaction turns out to be really long because you're going to be dividing up a bunch of stuff. All right, so there's that. Then KCl. Does KCl say it's aqueous? Yep, that means for the full ionic, I'm going to divide it up into its ions. What do you think is one of the ions that makes up KCl? Shelby, what's one of the ions in KCl? Huh? Okay, yeah, no problem. Let's, Will Broadfoot, if I said KCl aqueous, I want you to break it up into its ions. What's one of the ions you would break it up into? K, good. And what's K's charge? +1. So I'll just put plus after it and AQ. So we're doing the same thing we did earlier this week, or last week, earlier this unit, where it looked like this. And we had to break it up into like K plus AQ. But instead, we're just doing it underneath it instead of out the side of it. So we're doing the same thing. You're breaking it up into its ions. And then we get to our reaction arrow there. So we took everything that was aqueous on the left side, and we broke it up into its ions, kind of like we did last week, but now we're just writing it underneath it. On the other side of the arrow, I've got AgCl. Does AgCl say AQ after it? No, it does not. That means it's a solid and it does not dissolve, so it stays together. You just copy it just like it is there. What about KNO3? Does that say AQ after it, Vivi? Yeah, it does. So I've got to break it up into its ions. All right, so what's one of the ions that's part of KNO3? Maddie, what's one of the ions of KNO3? K plus is there again. So just like before, we'll say K plus AQ. Oops. And then remember, nitrate is a polyatomic ion. I ran out of room on the screen. I'll have to write right underneath it here. I would like to write this to the right of this, but I'm out of space. Plus, keep nitrate together. Oh, what's the charge of nitrate again, Jonathan? -1, good job. And then I'll put AQ after it because it's dissolved there. This is called the complete or full ionic equation. I've divided everything up. And the reason I do this step is because this helps me see things that cancel out because they're exactly the same on the left side and the right side. When I cancel things out, I'll have what's called the net ionic equation. Is there anything that appears exactly the same on the left and the right? Claire, do you see anything that appears exactly the same on the left and the right side of that arrow? Potassium, good. It's K plus on both sides. It's just K plus AQ. So those are things that I actually will get to cancel out. When something cancels, it becomes what we call a spectator. It means the K plus never really bonded with anything. It was really just floating around in solution the whole time. Parker, do you see anything else that is exactly the same on the left and the right-hand side? Yeah, good. Nitrate is our other spectator. So the things I'm marking out are called spectators, or spectator ions. They're usually ions. They weren't really involved in the reaction. It's just you couldn't get any you couldn't get any silver without some nitrate attached to it. You couldn't get any chloride without some K plus attached to it. So they had to be brought in to get the reaction kind of started, but after you got everything mixed together, it's just the Ag and the Cl that are actually bonding and reacting there. So what we have at that point, again, it's all here on the PowerPoint. The ionic equation was the one that we took all of our strong electrolytes, so all the things that said AQ after them, and we had dissociated them into their ions. So that's what we did a second ago. And then the net ionic equation is where we crossed out the NO3 and the K+. They did not change from the left side to the right side of the arrow. The things that crossed out are called spectator ions. They do not make or break any bonds over the course of the reaction. So they're like the spectators at the basketball game. They're not going to score any points. They're not going to do anything in the game. They're just also there. Some questions will ask you to identify the spectator ions. So you would say, oh, the spectator ions are NO3 minus and K+. Other times, they may just want you to show the net ionic equation. So this is what we call the net ionic equation. And it's important because now we can really see what is taking place in the actual chemical reaction without the mess of the spectator ions that are just kind of extra stuff there that get in the way of seeing the actual chemistry taking place. For precipitation reactions, the net ionic equation is usually going to focus on that precipitate, the precipitate actually forming from its ions. But you can also do net ionic reactions with acid-base neutralization, and you can do it with lots of the oxidation-reduction reactions. Not all of them, but lots of them. I've got these steps listed, just kind of a step-by-step method, because sometimes it's nice to go back and have some steps to follow. So first of all, the first step is often done for you. It says write the molecular equation. Well, half the time the molecular equation is given to you in the first place. Sometimes it might say it in the form of a sentence, and you have to figure out what the equation is. Number 2, dissociate all strong electrolytes. So that's what we were doing when I said, does it say AQ after it? What ions does it break up into? That was step 2 that we were doing there. And then step 3 is an easy step once you've done that. Cross out anything that remains unchanged from the left side to the right side of the equation. So I saw that K+ was on both sides, it could cancel. NO3 was on both sides, it could cancel. That was step 3. And then step 4 is to just write the net ionic equation again with everything that remains. So we just write it nice and neat after those things have canceled out. All right, so let's try this one. Acid-base neutralization is another type that we can write as net ionic equations. I'm not sure if this is on the back or if it's got its own. Yeah, it's got its own slide there. I'm not sure where that single. I guess it comes next. So this one's on the little slide here. If you just want to do it with me in the little box, or you could just do it on your notebook paper just as easily. So I've got KOH and HClO3. For some reason, I put the base first, but it's base plus acid we're seeing here. The first thing we want to do is figure out what are the products, and then we'll start dealing with dividing up the ions and then crossing things out. All right. So anytime you have an acid-base neutralization, the same thing is taking place here as any other kind of double replacement. K is going to get with the ClO3, right? H gets with OH. Acid plus base is going to yield salt plus water. All right, so if those two on the outsides come together, Davis, what would one of my products be here? H2O. You went with H2O first. Good for you. So we could do H2O. That's where the H and the OH have come together. All right, what's my other one going to be then? AC, what's another product going to be here? You got it. Good job. Potassium, we would call that potassium chlorate, KClO3. All right, now remember, if we're going to break this stuff up, we need to know whether these things are aqueous or not. All strong acids and strong bases are aqueous. So if I know my strong acids and my strong bases, I know those are going to be aqueous, AQ there. All right, now here comes a rule I want you to pay attention to. With H2O, put liquid after H2O whenever you see it in a reaction like this. Sometimes people want to put AQ after it because they're like, well, it's water. Water dissolves in water. But water actually formed here. I know some in an English class or something, they used to always have a debate over, is water wet? Or you might have heard people talk about that. And I would always say, no, water is not wet because water is water. Water makes other things wet. Well, in that way, you can kind of apply it to this. And they actually talked about this when they also were talking about it in English class. Water itself is the liquid, is the molecule water. So when you put water in water, it's not really dissolving in water. You're just putting water on top of water, right? So in that way, water, H2O, when you have H2O in a chemical reaction, you're going to put L after it. It's liquid water that formed. It's not dissolved water in water. So whenever you form water, we'll call it liquid here. All right, and then with your solubility rules, if you know solubility rule number 1 for our last thing here, KClO3, Mackenzie, is KCl, if it's got a K in it, does that mean it's going to be soluble or insoluble? Good job. That's rule number 1 says group 1 metals are going to make things soluble there. All right, so we've got our molecular equation. Then we're going to divide it up into the full ionic equation. So this is what we were doing together on that last one. If it's aqueous, I want you to break it up into its ions for the full-on ionic equation. So KOH, it's aqueous there. Pavitra, what do you think KOH would break up into when dissolved? Good job. And we'll put the charges on it, so we'll call it K plus, OH minus, it's hydroxide there. Next we've got HClO3. All right, it's aqueous there. It's a strong acid. Adam Peel, what do you think HClO3 breaks up into when dissolved? Good job. H plus, be sure to include the charge there, plus ClO3 minus. All right, and this is why it's important to put L after water. H2O is not aqueous, so it's not going to break up, meaning you write it exactly as it appears there. So you write it as H2O liquid. And then always run out of space here. MK, we've got KClO3. What's it going to break up into? Good job. So if I had more room, I would write this to the right side of it, but I ran out of room. All right, is anything going to cancel here? Anything exactly the same on the left and the right? Kira, what do you see that looks like it could cancel? Potassium, K plus. That means it's a spectator. All right. What's something else, Joseph, that looks like it would cancel? Chlorate. Chlorate, good job. I don't see anything else that cancels after that. So we're left with our net ionic reaction, which we'll do underneath that. Looks like we just have hydroxide plus hydrogen ion. And what does it make? Shelby, what's the only thing left on the right side of that arrow? H2O liquid. There's our net ionic reaction. And we can see it's really simple. Hydroxide and H plus are coming together to make H2O. The K plus and the chlorate, they were just the other half of the strong acid and the strong base. They never really did anything in terms of making or breaking bonds. And it turns out, guys, listen to this. For acid-base reactions, neutralization reactions, this is going to be your net ionic equation pretty much. It's always going to be some form of H plus and OH minus coming together to make water. That's the actual reaction that takes place with the acid-base neutralization. All right, I want to power through these notes, but you won't have homework after this, okay? So then we'll practice this stuff more tomorrow. So I want us to go ahead and get started with our last type that we want to do for net ionic equations, just to see that we can do it with one more type of reaction, or at least start it with one more type of reaction. Single replacement reactions will also do net ionic equations with these guys. But you do the same exact steps. First, you predict the product, so you have your molecular equation. Then you break up the things that are AQ or aqueous, and then you'll see what's left and what cancels. So with single replacement, we're going to have to check our activity series to see if something gets displaced or not. So pull out that old activity series and compare those two metals. I know gold's at the bottom. I know lithium's up top. Potassium's somewhere in there. Copper is somewhere in there. Will Broadfoot, did you find yours yet? Okay, well, I kind of did an abbreviated one on the screen there. You can just look on the screen in general. Which one's higher, K or Cu? Potassium's higher, yeah. I don't know where exactly they are, but I know Cu's near the bottom and K's not near the bottom. So potassium is definitely going to be higher. That means I have a reaction here. All right, so that means K's going to come in here and kick out the Cu as far as the reaction taking place. So Vivi, what would one of my products possibly be here? It's going to be KCl. I don't want you to put the little 2 after it, though, because K is still positive 1 and chloride's still negative 1. So it'll just come together as KCl. All right, what gets left over then? Ainsley, what's left over? Cu, good. Cu's all by itself over here. Then when I write this, I want to be sure that I decide, okay, the compound that I form is aqueous. The metal that I form is solid. Get that to right. There we go. And now we've got our reaction. Let's balance this and we'll stop there. So I need to balance this reaction before I move any further. K looks good so far. Cu looks good so far, but Cl does not look good. What can I do to balance the chlorines in this reaction? Oh, we'll do that tomorrow. So get that one balanced, and then we'll pick up with this tomorrow, guys. You did a great